Hi, in this video, we're going to analyze this circuit here. It is a common collector amplifier uh, because the output is taken out from the emitter side. It's also known as an emitter follower, right? An emitter follower. So we're going to derive expressions for Zi, that's the input impedance seen from the input side, Zo, the output impedance seen from the output side, the voltage gain of the circuit, and the current gain of the circuit. All right. Now, we're going to use a transistor model. Typically, we would use the RE model, but in this case, because we're interested in on the emitter side behavior, it is a lot easier for the analysis if we use a T model instead. I'll show you what a T model looks like in comparison with an RE model. But just to remind everyone, the steps for doing AC analysis are the three here. Short all capacitors, that's C1 and C2, with zero all DC sources, that's the VCC at the top here, that becomes 0 volts. And finally, we replace the transistor with a model, either an RE, in the case of common emitter configuration, or a T model for this case. So just to remind everybody, if you don't already know, this is what a T model, that's on the right side here, this is what a T model looks like in comparison to our regular RE model. So the difference is in the location of the internal resistor. Okay, so if the internal resistor is on the base side, then the expression is beta RE. If it is on the emitter side, then it's just RE. All right. So because if you can imagine, if I were to replace this into that transistor, you're going to have the little RE in series with the big RE resistor there. All right. All right. So let's start. Okay. So first, this is our T model, right, to replace the transistor. Now let's have a look at both the output side, VO, and also on the emitter side. All right. So when we're converting to an AC equivalent model, we short C2, so therefore VO directly connects to the emitter. All right. And the ground is the other end of RE. All right. So you have to remember the collector here, because it is 0 volts for VCC. Then the top part of the collector is also connected to ground. So the top part of the collector is connected to ground. VO is from emitter to ground. So this would be looking like this, right? So you have the collector connected to ground, and then you have an output voltage that is across RE. Okay. And again, IO is defined just like in the original diagram. It is going up into the transistor, and it is opposite to the direction of IE, which is the emitter current coming down. Right. Next, we look on the input side. Well, it's fairly straightforward. VCC is going to be 0 volts, which means the top part of RB is going to end up ground, and the other side of RB will remain at base, and then C1 becomes a short. So, like so. All right, so you have RB that's between the base and ground, and you have the input signal and also the input impedance seen from this side going in. Now, if you've seen the analysis for a CE amplifier with a emitter resistance, there is a base current that a base impedance that we have to consider. All right, so that's basically, after RB, looking into the base, right? Looking into the base, there is an impedance of ZB, which we need to figure out later. All right, so let's start deriving our usual four components: IO, II, VO, and VI, and also to figure out what ZB is. All right. Okay, so first of all, IO is fairly straightforward, because IO is just a current flowing through RE but going upwards in opposition to IE. IE is flowing down, so straight away we can write that IO is equal to a negative beta plus 1 times IB. All right. So that's IO. All right. So now let's have a look at ZB because we want to look at II, but then to look at II, we need to understand what ZB is. All right. So let's have a look at ZB next. Okay, ZB is, as I've said, is the impedance seen into the base. So if you look at ZB here, you have an input current into ZB that is IB. So IB is flowing into our ZB interface, if you like. So IB is flowing in, and eventually you'll see these two resistors, and the current that flows through both of them is beta plus 1 IB. So therefore, you can define ZB as using Ohm's law. R equals V over I. The V here is going to be VI. That's the VI here. Okay, and VI is basically going to be the sum of the voltage drop between RE and little RE and big RE. Right, and the current, of course, is just IB going in. So let's just figure out let's write down what ZB is. Right. Okay, so for ZB, all right, so Ohm's law, ZB, oops, sorry. Okay, so ZB is, R equals V over I, so it's going to be VI, that's the voltage across the whole interface, divided by the current that is going into ZB, which is IB, right? And then we can restate VI as the voltage drop, the sum of the voltage drop across little RE and big RE, all right? So, again, using Ohm's law, V equals I times R. All right. So I in this case will be beta plus 1. All right. Plus 1 times little re plus big re. Okay. And that's pretty much it. That's pretty much what ZB is. Okay. Uh, you can simplify this further because there's one property that you should know by now. Because especially for discrete transistors, beta is much larger than 1. Usually is in the hundreds. All right. So therefore, we can write ZB, all right, as is equal to beta times little re plus big re. All right. Okay, so since beta is much larger than 1, so therefore beta plus 1 becomes insignificant, leaving just beta. So you're going to get that. So that's our ZB. So now that we have ZB, let's look into II. All right. Now for II, we're going to use ZB. We're going to use IB. So basically, you have II comes in and splits its current between RB coming down here and going into the base IB. So this is so I can write an equation for IB in terms of II using a current divider rule, right? Okay. All right. So the current divider rule. So we're going to write IB is equal to II times what? Well, it's going to be RB divided by RB plus ZB, right? So it's going to be RB divided by RB plus ZB. Okay, just oops. Okay. All right. So let's rearrange this so that we have an equation that is in terms of II. All right. So we can arrange it around. So move things around. II is equal to IB times basically is going to go to the other side, so the fraction will invert. So it's going to be RB plus ZB divided by RB, right? Right. So that's our equation for II. I just want to put IB on the side here. Okay. All right. So now we have IO, we have II, we have ZB. Now let's have a look at VO. Well, what is VO? Well, VO is basically looking from the right towards RE. All right. So this is just a straightforward Ohm's law. All right. However, the current that we need to use is IO, and IO is pointing in the wrong direction. Well, not in the wrong direction, but in the opposite direction to where it should be if we want a VO that is positive. All right. If we want a VO that is positive, IO needs to be going downwards. All right. So this is using Ohm's law again. An expression for VO. Is going to be equal to B equals IR, so it's going to be IO. Sorry, negative IO, my bad. So it's going to be negative IO times RE, right? And let's just straight away replace negative IO replace IO with this term here. Okay, so what you're going to get is a negative negative, so which means it becomes a positive, right? So negative RE. Okay. Okay, basically becomes just beta plus 1 times IB RE. Okay. And again, that approximates to, because of beta is much, much larger than 1, becoming just beta times IB RE. Okay. All right. So that's what VO becomes. So now let's have a look at VI. VI is basically, again, using Ohm's law. V equals IR. I is II. And R will be these two impedances in parallel. All right. So again, this is Ohm's law. So VI is going to be equal to II times the parallel of these two impedances. Oops, sorry. Okay. And let's just substitute II with what we've worked up here. So II is equal to all of that. Oops, sorry. Okay. And then multiply by the parallel of RB and ZB. Now I'm going to expand RB parallel ZB into its full term. So it's going to be RB ZB divided by RB plus ZB. All right. And this one and RB also cancels out. Leaving just IB ZB, right? Oops, sorry. Equals to IB ZB. All right. Okay, so that's VI. So I think we have everything now. We have the 4 IOII VOVI, so we can work out our first um, component. Let me just align this a bit. Okay. So let's work out the first one, ZI. Well, ZI should be pretty obvious. Um, Basically, it is just a parallel of RB and ZB, so that's the answer. That is ZI. All right, so next, ZO. Well, what is ZO? Well, ZO is looking from the right to the left across RE. And as usual, whenever we trying to work out what the output impedance is, we have to zero the input source, right? So the VI becomes zero. So when that becomes zero, the top part of this node, this node will end up connected to ground. All right. So that means this entire node is now ground. So you can imagine, which means IB is zero. When IB is zero, beta IB is also zero. That's 0 amps. 0 amps means it's an open circuit. So then what you have is the top of little re ends up at the bottom, right? So when ZO looks to the left, it's going to see big RE and little re in parallel, right? That's what ZO will see. So straightforward, ZO is simply little re in parallel with big RE, right? So that's ZO. So now let's look at the voltage gain AV. So voltage gain AV is defined as VO, the output voltage, divided by VI, the input voltage. And we have an expression for both of those. So this is VO. All right, so that divided by VI, this is VI. Okay. Oops. Okay. Uh, so let's expand ZB because ZB has a beta that can cancel out with that beta. All right, so let's do that. So you have beta IB RE at the top divided by IB times ZB. Now ZB is just this, so it's beta, and then little re plus big RE. Okay. Okay, so well, a lot of stuff cancels out. So beta IB cancels out. Top and bottom. All right, so what's left is just capital RE divided by little re plus big RE. Okay. Now, one of the characteristics of a common collector or emitter follower is that the output voltage more or less follows the input. So, and typically little re is much smaller than capital Re, by design. So, which means that in the end, it'll just be Re over Re, which is just one. So, typical gain is close to one. Yeah, it's close to one because little re is not exactly zero. So, the gain is typically close to one. All right. Now let's work out the last part, which is a current gain. That's AAI. All right, so that's just simply equals to IO divided by II. Okay, so we have an expression for both. So IO is this. Divided by II. So let me just open a bracket here. II is this. Close bracket. Space bar. Oh, good lord. Okay. Let me just take this and put it there. Okay. Finally. All right. Um, so again, you have a few things canceling out there. Okay, so one of which is IB, so let's cancel that one out straight away. So top and bottom, IB. Okay. And the other one is the fact that beta is typically much larger than one, so therefore we can simplify the top part to just simply be beta. So then the final answer is going to be negative beta. All right, and then this RB, I'm going to put it at the top. So apply by RB divided by RB plus ZB. Okay. Okay, so just for completion's sake, let's just substitute ZB into the equation. All right, so ZB is here. So let me just copy this again. Okay, and then find ZB and replace it here. All right, and nothing else can cancel, so that's the final answer. All right. So as I said before, the common collector or emitter follower is actually quite good as a buffer. All right, as a buffer stage because it has quite high input impedance and quite low output impedance, and a gain of one, a voltage gain of one. So it's good as a buffer. All right. Okay, that's it. That's it. Thanks.